All right, guys, welcome back to week 6 of CSM. Today I'm going to be talking about weighted quick union. And sorry, this is going to be like a more of a high level overview. So if you really want to get more in depth, I would highly recommend watching Hog's lecture videos. But yeah, let's hop into it. Okay, so yeah, first things first, we want to talk about disjoint sets as a data structure. So essentially, disjoint sets is an abstract data structure, and it has two main functions. So the first is going to be connect x, y. And then say we have some arbitrary x and we have some arbitrary y, and like obviously like these can be different, some sort of like way of connecting them. We're going to want to connect them through connect x, y. We call the function, and this is going to make some sort of connection. So like they now have some sort of relationship between each other. So then when we call is connected, which is the next function, we can say, okay, is connected x and y. And in this case, which will return true. But if we want to have like some value z, and we call is connected x and z, so connected x and z, this is gonna return false. And sorry, clean this up a bit. So yeah, is connected x z would return false. So yeah, let's kind of keep going. So yeah, here's another few examples. So if we want to know how to we can make this tree, like the first operation we'd call is connect 1 and 0. So yeah, we can see here, connect 1, 0, and then this would create this branch right here. The next thing we can call is connect 0 and 3. So yeah, we can see here that would connect 0 and 3. And then after that, we can call connect 3 and 2. So yeah, connect 3 and 2. And so yeah, basically that's kind of like a high level overview of like how to visualize how the connect operation works. And then the other thing is we can kind of redo this example of like, okay, well, is connected 3 and 4. We clearly see that there is no connection between 3 and 4, so we can return false. And then we can also do is connected 2 and 3, and we can clearly see that this line here is between 2 and 3. So then in this case, that would return true. So yeah, hopefully all that makes sense. So that's kind of like a high level overview on disjoint sets. And now we can kind of get discussing on like, how would I implement this? Because obviously it's a lot easier to be like, okay, well, there's no connection between 2 and 3. But when I'm trying to visualize that in code and I'm trying to translate that to code, it's a lot more difficult of a task. So yeah, let's hop into it. So yeah, here's kind of the question where it's like, how do we know each set belongs to each set? Yeah. So yeah, okay, let's hop into it. So the first method I want to bring awareness to or kind of just talk about is quick union. So in quick union, you're going to want to create an array, and in each and then in this array, each index is going to correspond to a value, and you're going to assign each index to track their parent. So now, I mean, I think that can be easily like kind of hard to understand what I just said. So let me kind of get into an example and maybe it'll make a little bit more sense. So say we have this like quick union data structure right here. It may also be a little easier to visualize it vertically. So I can also draw it out like this. 3 and then 2. So yeah. So for example, we're going to start with 2. Let's just start from the bottom up. Should make it a little bit more sense. So we can see here that 2's parent is 3. Sorry, it's a little bit of a messy 3, but I'm just gonna write 3. Shoot, 3. So yeah, we can see here that 2's parent is 3. So in this array, actually, sorry, this is a typo. My bad, guys. So in this array, in index 2, we're gonna have a pointer to 3. And so basically that's going to say, okay, the next connection is like pointing to 3. So it's going to point to index 3. And then we have 3, which is in the next, which is like the parent of 2. So we go up to 3 and we say, okay, like what's your parent? And we can clearly see that this is 0. So we have this connection. So we have the pointer to 0. So this points to index 0. We keep on going up. We say, okay, 0's parent is 1. So we say, okay, this is 1. And then the next more tricky part, maybe, okay, what do we do when we have something like 1 or even like 4 in which there's no parent? So in this case, in quick union, we're just going to write -1, and this symbolizes there's no parent, and this is the root node. So yeah, here's kind of oh, and then the next thing about quick union is now like, what if I have, you know, this tree like 1 0 5 2 and 6 3 and I want to connect 2 and 3. So now like your first instinct may be like, oh, let's just draw a connection between 2 and 3. So like something like that. And actually, we're not going to want to do this. And the reason being we don't want to do this is because if we do this connection, we'd have a tree that looks something like this. 0, 5, 2. And then I guess we get a little tricky with like the way in which like 3 and 6 would switch, but I guess we could say like something like this. So like as we can see here, we have a height of 1, 2, 3, 4. And that's like yeah. So we have a height of 4. And clearly here, we know that this, because we know with disjoint sets and weighted quick union or quick union in general, the runtime is log n proportional to the height. We know that we want a smaller height. So instead of doing something like this where we get a bigger height, we can instead do something like this where we find the root node of 3. So we can kind of ignore this also. I'll just white it out just to make it easier to visualize. So yeah, so instead of doing what we did earlier, we can instead find the root node of 3, which in this case would be 6. So yeah, find this root node. And then we want to connect that to 2's root node, which would be 1. So you can see here, this would be the current connection. And in doing so, now we know that this is 1, 2, a height of 2. So it's a much smaller tree. And yeah, it'd be a much more efficient runtime. And so yeah, that's kind of like why we want to connect the roots instead of just like connecting 2 nodes directly in quick union. So the next part is going to be talking about weighted quick union, which is basically like a way to even more, even like further optimize quick union. So yeah. Oh, and I guess I'll talk about, so going back to this slide where we kind of talked about like how we keep track of these in the array. Basically, I'll kind of run through it now. So basically, we'll set up an array of 6 because we know, sorry, size 7, but 6. So yeah, we set up this array here. Sorry, it's kind of overflowing in the page. So 1, 2, 3, 6. And I guess I can't count. Sorry about that. So yeah, this is going to stay the same. This is going to stay the same. This is going to stay the same. And this is 3 will actually stay the same because it'll still be connected to 6. So it'll be 6. 4, we know that we made no different connections to 4. And then the next one is going to be 5. 5, we also know will stay the same. So this will stay to 1. And then 6 will be the one where it really changes. And instead of being -1, we now know that it's connected to the root node 1. So we can see like through here, this connection, its parent is 1. So we're going to say 1. And hopefully that all makes sense. Okay, so now we're going to talk about weighted quick union, which is basically a way to optimize quick union. And in essence, in weighted quick union, you're going to want to link the root of the smaller tree to a larger tree. So I've kind of gone through an example here. So if we have 2 trees, 2 and 3, and then we have 1, 0, you know, those values, we would, instead of doing this, where we do something like that, and it's going to be bigger, we can instead do this, where we link it here. So yeah, I hope that makes sense. And we can kind of get more into like how this will be implemented. And so essentially, it's pretty similar to quick union in the sense that you're going to want to have an array that keeps track of each one's parents. And then there's going to be negative values associated with each root node. Except in this case, instead of having -1 as the root node is going to be a negative weight value. So for example, we have this here. So we can see here that there's 1, 2, 3, 4, 5. So we can look at, okay, index 1. We know that's the root node from earlier, and we know how that works. So yeah, we can look at index 1, and we can see, okay, this is going to have a weight value, or it can have a value of -5. And it's a negative because that represents the root. And then the 5 is going to represent the weight of the tree. And then similarly with 2 and 3, we can see here that there's 2 values. And so yeah, it's going to have -2. And then the rest is all going to stay the same. But yeah, this is kind of like more of a way you can like implement this in code, and it'll make it a lot easier. So yeah, now that we kind of have that high level overview, let's hop into the question. And yeah, I hope everything makes sense. And yeah, let's do the question. All right, welcome back. Today I'm going to be walking through question 2, weighted quick union. And yeah, let's hop into it. So the first way I would approach this problem is by first breaking down what we have and the methods and functions we're given. So let's go into this weighted quick union class. So for starters, we have this parent array, and it says each node's index in this array contains the index of their parent node. So this is kind of like what we broke down in an earlier video. And yeah, so hopefully this makes sense. If not, I would recommend referencing the early part of the video. So yeah, so the next part, we have this constructor, and it's basically saying, okay, if we have, say, something like size equal to 3, it's going to initialize this new parent array to be an integer array of size 3. So it's going to look like this. And then from there, it's going to go through each one and set it all to -1. And the reason this may make sense is because originally they're all going to be unconnected. So they're all going to have no parents. So they're all going to be kind of like floating out like this, just like 1, 2. So this is like more of like a visual example. So yeah, so the next method we have is find root int of x. So for example, if we have something like, I don't know, maybe like 1, -3, and then 0. And the reason I chose -3 was because we have 1, 2, 3 values, so weight of 3. And that's important for weighted quick union. So yeah, we have this. We say, okay, let's set the root, or sorry, let's say we do find root. Let's say we do find root 2, for example. So originally root is going to be equal to 2. We're going to say, okay, is parent array root greater than or equal to 0? We clearly see here that it would actually be equal to 0. So we then go into the while loop. We set root equal to 0. And we do the same check again. We say parent array root. And we'd see this would be equal to 1. So then we'd set root equal to 1. And then we do one last check. And we'd actually see this is -3, which is less than or equal to 0. And so then this would return -3. Or sorry, this would not return -3. This would return 1. And I think important distinction that I almost made I just made a mistake of is that it actually returns the index value of the root, not the value itself. So yeah. The next thing we're going to be implementing is connect. And then the next method is connected, which basically just looks for the root and then sees if they have the same root. And we know because of weighted quick union that they're going to be connected through the roots. So yeah. Or I'm sorry, I misspoke. In weighted quick union, basically they'll have the same roots if they're connected. Sorry about that. So yeah, let's get into the question. It basically says implement connect for union tree such that for nodes x and y, the root of the node with the smaller size union becomes the child of the root of the node with the larger size union. If they're equally sized, make the child of the root of x the child of y. So obviously that's a lot to take in. So let me kind of break down an example. So say we have something like this where we have 2 trees, 1, 2, 3, and 4 and 5, and we'll say this is x and this is y. So in this case, we're going to want to connect. Say we're just saying connect 3 and 5. So instead of directly connecting like this, we're instead going to want to connect like this, where we take these, draw a little space. We're basically going to want to connect the root of 5, which would be 4, and then the root of 3, which would be 1, since we know we can visually see that y is a smaller tree than x, we're basically going to want to connect the root here. So yeah, hopefully that makes sense on why that works and conceptually like understanding the problem now. So yeah, let's kind of get into it. So I think the first really important thing to think about is, so how are we making these connections? We want to think about like what we're using. So clearly here we know with weighted quick unions, we want to use the weights. We want to use the weights of each tree, and we connect the smaller weight to the larger weight. And the other thing to notice is that we're not using the value 5. We're using the roots, and we're connecting each roots together. So I think the important thing here is we know, okay, we know we need the weights, and we know we need the roots. And we actually know that through finding the roots, we also can find the weights. So I think the first two variables here are probably going to be the roots, finding the roots. And we know we have this method from above that we passes in some like integer, and then it finds the root and it returns the index value of that root. So find root x. Oh, sorry. Let's make this int root of x, int root of y, and find root y. So yeah, hopefully that makes sense why that's pretty important to the problem. And yeah, so let's keep going. So the next thing we can do is we have this if else statement. So let's kind of think about these two cases, and they give us it here. So they say implement connect for union tree such that for nodes x and y, the root of the node with the smaller size union becomes the child of the root of the node with the larger size union. So we have two cases here. So the first case is that the weight of x is greater than the weight of y. The second case, which would be the else statement, is the weight of y greater than the weight of x. And as I mentioned earlier, we know that with the root contains the weight of each tree. And the one thing to note about this is that while the root contains the weight of each tree, we know that this is contained in a negative value. So when finding this weight, we have to negate it to get the positive. So yeah, hopefully that makes sense. So we have the index through here. We have the index of root of x and root of y. So let's say, okay, so if the weight, we get the weight of x, and if this is greater than or equal to the weight of y, then we do something. And to kind of like just more concrete formalize this, say the weight is -6 in x, and then